You know that classic question every kid asks at some point? Why is the sky blue? It's literally the most foundational science question out there and one we all absolutely assume we know the answer to. But what if I told you that the standard textbook explanation we've relied on for over a century is actually fundamentally flawed when you really look at the math? Welcome to The Explainer. Today we're unpacking a highly fascinating research paper by V.V. Samak and M.N. Schneider called Different Perspective on Blue Sky Theory. Okay, let's dive right in and start questioning everything we thought we knew.
So think back to, middle school physics. The standard answer to this question revolves around a concept called Rayleigh scattering. Back in the late 19th century, Lord Rayleigh proposed that sunlight hits the Earth's atmosphere, and the gases up there scatter the short blue wavelengths much more efficiently than the longer red ones. That blue light bounces around, hits our eyes, and boom, blue sky. It sounds perfectly neat and tidy, right?
Well, here's where this research basically pulls the rug right out from under us. The paper states that the classic Rayleigh scattering model and the related Thomson model are actually incompatible with modern quantum physics. Basically, Rayleigh came up with his theory decades before quantum mechanics or even the concept of the photon were invented. And, as you'll see, when you apply modern quantum rules to his century-old math, things start to completely break down.
Just look at this glaring paradox. If you actually run the numbers using Rayleigh's exact formulas, multiplying the sun's spectrum by his scattering formula, and then filtering it through human eye sensitivity, the math predicts a peak right in the middle of the visual spectrum. According to established, unquestioned science, the sky above us shouldn't be blue at all. It should literally look like a giant glowing green lawn. Crazy, right?
Section 1. The sunlight intensity problem. So, where exactly did Rayleigh's math go off the rails? It really all comes down to how we define light. Rayleigh assumed light was an infinite, continuous wave, mainly because the concept of a quantized photon just didn't exist yet. To understand why that's a huge issue, compare a highly focused laser beam to everyday ambient sunlight. In a laser, the intensity is incredibly high, meaning billions of photons overlap. They act like a continuous wave, which is exactly where classical formulas perfectly work. But sunlight? It's much more like a sparse trickle. The photons arrive individually, one by one. This contrast highlights the exact physical threshold we're talking about here. Notice the high-intensity overlap of photons on one side. But for visible sunlight hitting our atmosphere, the energy density, or spectral irradiance, is about 1,000,000 times too low for photons to overlap. Sunlight is strictly a single photon environment. It's interacting with the nitrogen and oxygen in our atmosphere, one tiny isolated particle at a time.
Section 2. Anatomy of a photon. To truly understand these microscopic collisions, we have to map out the 3D structure of light itself.
Samak and Schneider revive a concept originally defined by physicists in the early 20th century called a Welle-Zug, which translates to a wave packet or wave train. In this model, a photon isn't just some infinitely tiny point, it's a distinct burst of electromagnetic radiation emitted by an atomic oscillator. It has a specific physical length and a distinct duration in time. It's a real 3D object. Let's look at the time domain first. When an atom spits out a photon, it doesn't happen instantly. It takes a tiny fraction of a second. And notice how the temporal structure of a photon is modeled. The electric field starts really strong and then decays exponentially over time. This decay time is actually what gives the photon its distinct natural spectral line width. And in physical, three-dimensional space, the mental model looks something like this. It's a localized packet moving forward at the speed of light. Transversely, the electric field is distributed in a Gaussian shape, so essentially a bell curve that's thickest right in the middle. The really crucial detail to remember here is that the transverse radius of this photon is roughly half of its wavelength. Section 3. The ultraviolet energy threshold. This is a strict physical limit that basically breaks standard scattering theories.
Okay, so the core point is this. In quantum mechanics, an electron inside an atom can only re-emit a photon, which, by the way, is all scattering actually is, if it is forced into a mechanical oscillation that matches or exceeds the energy of the incoming photon. If the incoming photon just doesn't have enough energy to jolt the electron that hard, the electron simply cannot scatter it. It's a strict physical threshold, no exceptions.
When they crunched the data for the nitrogen and oxygen molecules that make up 99% of our atmosphere, they found something completely shocking. The threshold for scattering requires photons with a wavelength shorter than 350 nanometers. This means visible light, red, green, and yes, even blue, simply does not have the energy to bounce off the atmosphere. According to this model,
Only invisible, high-energy ultraviolet photons can actually scatter. Visible sunlight just cuts straight through to the ground without scattering at all.
Section 4. Why the sky is blue. It's time to solve the paradox.
So this introduces a massive mystery, right? If only invisible UV light scatters, why isn't the sky just pitch black to us? Well, the research proposes a brilliant new causal chain to solve this without violating quantum mechanics. First, the sun emits light. Second, those high-energy, invisible UV photons hit the nitrogen and oxygen and scatter. But here is the absolute magic step. Third, during that collision, the photons actually lose a tiny bit of kinetic energy to the electron. And fourth, because energy and wavelength are linked, that slight drop physically shifts the photon's wavelength, dropping it right out of the invisible UV spectrum and exactly into the visible blue spectrum.
And the math backs this up beautifully. This downward curve perfectly illustrates the residual energy transferred from the photon to the electron. Classical physics assumed absolutely zero energy was lost in this transaction. But this new model shows energy bleeding off, which causes a reddening effect, a lowering of the frequency. And this energy loss is highly dependent on the starting wavelength of the light.
Let's see how this maps onto the real world. Think about looking straight up into the sky at noon. The scattered UV photons travel about 10 kilometers through the atmosphere to your eye. In that short path, they bleed just enough energy to shift into the blue spectrum. But check out a sunrise or sunset. At dawn or dusk, light travels a massive 100-kilometer path through the atmosphere. Over that huge distance, the scattered photons keep bleeding more and more energy, shifting from blue past green and all the way down into the reds and oranges. It perfectly explains the color gradient of our sky based entirely on the distance the photon travels.
Section 5. Rethinking the universe. Because the cosmic implications of this discovery are huge.
If this physical mechanism is true right here on Earth, it forces us to rethink the vast depths of the cosmos. I mean, if classical scattering theories have been wrong for 100 years about something as basic as why the sky is blue, what else have we gotten wrong? This single-photon energy loss model directly challenges one of the most unquestionable, foundational pillars of modern astrophysics.
The paper introduces a concept called electron-Engable Dampfpunkt. Try saying that 3 times fast, right? It simply translates to photon energy loss, to intergalactic free electrons. See, we know that the empty space between galaxies isn't actually entirely empty. It's sprinkled with incredibly sparse, free-floating electrons. So as light travels billions of light years across the universe to reach our telescopes, it's constantly colliding with these free electrons.
The research boldly concludes that this new theoretical model predicts a completely alternative explanation to cosmological redshift. For decades, we've observed that the further away a galaxy is, the redder its light appears. The entire theory of the Big Bang and the expanding universe hinges on the assumption that this redshift is caused by galaxies physically flying away from us, stretching the light out like a giant Doppler effect.
But this paper presents a staggering alternative. What if the universe isn't expanding at all? What if light traveling across billions of light years of space is simply bleeding tiny bits of kinetic energy to free electrons along the way, just like it does in our own atmosphere? Is the universe actually expanding, or is the light reaching our telescopes just getting tired? It's a deeply provocative question that turns a middle school physics lesson about a blue sky into a fundamental challenge of our entire cosmic origin story. And that is an idea absolutely worth exploring.